Okay, so welcome to Math383 Complex Analysis. So this is lecture 6, and what I want to do today is talk about Cauchy's formula and consequences. So whoever's keeping the count, Cauchy gets another +1. So we're going to do some level of proofs of Cauchy's formulas. We will see that the words holomorphic and analytic are the same. So analytic, what does that mean? So analytic, you have a power series that converges to the function. And remember, we have this terrible function, e to the 1 over x, negative 1 over x squared. So Taylor series converges for all x, but not to our function. Complex analysis does not allow something like this to happen. Complex analysis will not allow you to have a function that is differentiable that does not equal its Taylor series. But you can have a Taylor series that converges pointwise and is never equal to your function other than at 0, which is no big deal because your Taylor series is f of 0 plus multiples of powers of x, which is clearly going to be 0, 0. And then, if time permits, we'll apply Cauchy's formula to do some integration. So we frequently have choices in the contours we use, and we'll talk a little bit about, maybe which contours do we want to use, and we'll see why we impose certain conditions. Right. So just to review, you should have memorized at this point Gaussat's theorem. We started by talking about if we have a primitive and we have a nice region and we integrate over a curve, then as long as it's a closed curve, the integral is going to be 0. And this was our parametrizing. We have the antiderivative at the endpoint minus the antiderivative at the starting point. Well, the starting point and the endpoint are the same. So if there's a primitive, the integral is 0, not a big deal. And we started by proving things for triangles. Right? Triangles are wonderful shapes. They fit together nicely. And after a triangle, what did we extend this to? Rectangles, which can be written as sums of triangles. So we know things for rectangles and triangles. We then proved that if we have a function that is holomorphic in a unit disk, or any disk actually, doesn't matter by scaling, that we can construct a primitive, and we did this by like a grid walk. We walk east, then we walk north. You could actually do this in a slightly more general set than a disk. If I give you an ellipse, that would work there as well. If I give you a nice convex set, if you know about this notion of simply connected, if they did that in real analysis, this like a path connected notion of connectedness. As long as I can get 2 points, I'm in pretty good shape. But I want to have no holes in my region. And so when I start to have holes, there are some dangers. And so the big result we had is that if we have a holomorphic function, we can essentially define a primitive. Once we define a primitive, everything is going to be nice and integrals will be 0. And it's important for the function to be holomorphic, not just on the curve or in the neighborhood of the curve, but also in the interior of the curve. That there's no place where it blows up. As soon as it blows up in a place, then strange things can happen. So if I have a path connecting 2 points, say z0 and z, if something is blowing up over here, that's okay. I can stay away from this blow up. I can draw things around here. Everything is going to be fine. I'll just try to sketch a little bit of here are some possibilities. So if you look at the first shape in the upper left-hand corner, I've got some rectilinear path, some polygonal path, but there is a hole in the region. And it's possible that maybe my function is holomorphic in the donut, but not in that big center. And so if that's the case, I could have a function that's differentiable, but I don't know that the integral over the curve is going to be 0. Cool. So can somebody give me a function that is differentiable in the donut, but not in the center of the donut? So what's a function that's not differentiable if we look at the filled-in thing? Yes. Not maybe. 1 over z, right? We showed that 1 over z, if you integrate that along a circle, it is not going to be 0. And so the function 1 over z is holomorphic in the donut. It's absolutely differentiable there. So it's good that we can look at a simple function like this and start building some intuition as to what could go wrong. And so it's not enough if you're holomorphic in the region, it's got to be in the interior of the region as well. Now, the idea in the second picture in the top row, the one in the center, is that maybe what we can do is try to reduce things to local problems. On small little local patches, I want to just draw a bunch of circles and see what's going on in each of these circles and somehow pass knowledge around. And I'm going to elaborate that on greater detail in a second. In the one in the upper right corner, I've got a bunch of circles moving all the way around. And as I stay away from the place where the function has a pole, it turns out we can get Cauchy's theorem there, that the integral will be 0. Equivalently over here, we have two curves, gamma 1, gamma 2 in the bottom left. I can pass from gamma 1 to gamma 2 by deforming the curves. I can move from gamma 1 to gamma 2, staying entirely in the region. This is where the class can become exceptionally painful. So there's a beautiful theorem that a simple closed curve, a closed curve that doesn't intersect itself, splits the complex plane into two regions, the interior and the exterior. This is called the Jordan plane curve theorem. It is remarkably easy to state. It is extremely intuitive. There is a proof of this in the back of the book if you want to see just how bad it is to prove something like this. And so I do not want to go the topological route. I would much rather do number theory and other types of applications to physics. And so we will always be looking at nice curves where we can just look at it and see, yes, I see how to pass from one to another. But you can make this more rigorous in terms of just what properties curves will have and how we can pass from one to the other. So doing things a little bit more explicitly in the next picture, here I have two curves, and let's make one curve the red curve and one curve the blue curve. So I'll make the bottom the red, and I'll make the top one the blue. And what I want to show is that integrating along the blue curve is the same as integrating along the red curve. Or if I look at this unified curve where I start at, let's say, the green dot and return to the green dot, I want to say that that integral is going to be 0. That, I have a simple closed curve, and I want to say that the integral over the simple closed curve is 0. Well, if I draw a bunch of circles that overlap, let me see what's going on. So let me look at the first circle on the bottom right over here. And so what I can do is I can start breaking my segments up into little pieces. And so over here, I'm adding this extra line, and I'm going to go through this line twice. Once to make the bottom, can we say generalized triangle? It has 3 sides. So we'll call this a generalized triangle. And then I'll go through it in the other direction. And now I have a nice simple closed curve. What's the integral over this simple closed curve going to be? 0, because I have a primitive in there because I live inside a disk. And so because I have a disk, I know the integral over the small red part plus the yellow part plus the blue part is 0. When I go to the next one, I now have a generalized rectangle. And again, this is going to live inside a disk. And I'm going to now take that yellow piece, and now I'm going to go over it in the opposite direction, so we'll cancel out from the previous. And so as I march all the way down, all of those interior sides will cancel. And at the end of the day, I will get the integral over the red plus the integral over the blue is 0. So the integral over the closed curve is 0, or equivalently, the integral over the red is the integral over the blue. It doesn't matter how I got there. It just matters, where do I start, where do I end? The value of the integral is independent of the path. So if you remember your multivariable calculus, if you remember some of your physics, there's a lot of wonderful connections with stuff like that. It's extremely important that I am able to have a sequence of disks covering the two curves. And what you might have trouble doing it. Maybe I have a bunch of different curves. And so earlier we looked at, do we have it? Yeah, okay. So it was on the next page. So I could have maybe a bunch of curves. And I could first show the integral over the bottom curve is the integral over the one above the bottom curve. And then the integral of the one above the bottom curve is equal to the integral of the one above the bottom curve. And just slowly push things up like this. The question is, what level of rigor do you want? I'm a theoretical math professor. You want me to bring it, I'll bring it. I think this is a good enough level to get a sense of what is going on and why this is true. But if people want, I'm absolutely happy to go into excruciating, painful detail on all of this. Okay, but this is essentially what's going on. Is if we have regions that are nice and the function is holomorphic in the entire region, then the integral over a closed curve is 0. And so it only matters where we start and where we end. Okay, now let's start getting to the truly remarkable theorems of complex analysis. And so the first one is, suppose F is holomorphic in an open set that contains the closure of a disk D. And let's C denote the boundary circle. Then the integral over this boundary curve of the function f, so we'll do f of zeta over zeta minus z. So note that zeta lies on the circle C. And I divide by 1 over 2 pi I, this equals f of z. This is absolutely amazing. What it's telling you is, imagine I tell you the values of this function on the boundary, on this unit circle. And I tell you that the function is holomorphic. Once I tell you this, there is only one way to extend the definition of f from the boundary to the entire space and be holomorphic. It's uniquely determined. So specifying the boundary condition, specifying what f is on the boundary circle C, is enough to tell you what f is everywhere. So truly remarkable. Okay? Yes?
Is it only for Z inside?
For Z inside the disk.
How about outside?
Outside, I'm not saying anything. So for Z inside the disk, so if I'm inside the disk, I'm in a place where everything is nice. Now, is the function f of zeta holomorphic? Is f of zeta holomorphic? Yeah. From the supposed f is holomorphic. So, okay, f of zeta is holomorphic. What about 1 over zeta minus z? Is 1 over zeta minus z holomorphic? Or does it have a problem? Yes.
It's got a singularity at zeta equals z.
Is this good news or bad news?
That's good news.
It is good news, right? Otherwise, everything would just be 0. So the fact that it has a singularity, we have hope to see something. Okay? So we're going to somehow exploit that. And the goal in this beautiful picture on the right is you can see that little dot z where things blow up. And what I want to do is I want to replace integrating over the big circle C with integrating over a small circle of radius epsilon about the point that blows up. And so I'll go around the big circle, I'll then come in, go around that point Z in the opposite direction, I'll go around clockwise, then I'll come back out and continue going around my outside boundary. And of course, those two straight line segments are going to cancel as the thickness goes to 0. And I'll be left with the integral over big C is equal to, plus the integral over the circle of radius epsilon going in the wrong direction, going clockwise, is equal to 0. So the integral over the big circle will just be the integral over the small circle. Well, if zeta lives on the boundary of the circle, far away from Z, this is not a big deal. As we get closer and closer to Z, what is f of zeta going to get closer and closer to? I'm sorry? F of z. So on that small circle, the function f of zeta is not going to change that much. The zeta minus z might be changing a lot, but the f of zeta should be approximately constant. And so the hope is that we'll be able to do the small integral and then show that this is equal to the large integral. So what we want to do now is we want to start doing some of the calculations. I want to make sure I do things correctly. Okay, so we know the integral over c of f of zeta over zeta minus z d zeta equals the integral over the circle of radius epsilon of f of zeta over zeta minus z d zeta by what we just said. And I could have the 1 over 2 pi i's, but that's, not really necessary. Okay, is everybody comfortable with that? Yes.
So just to clarify, the C epsilon is like the keyhole picture with.
Yeah, so C epsilon is a circle of radius epsilon centered at Z. So here we can write zeta as Z plus, say, epsilon e to the I theta. So is everybody comfortable with this? Yes.
Can we specify like epsilon is small? Or-
Epsilon is small. So epsilon is always going to be a small number tending to 0. This is convention in mathematics. So whenever we say epsilon, epsilon is always a small number tending to 0. So we're taking a smaller and smaller circle.
But in the statement of the theorem, it doesn't specify how large.
Right, so I mean, C is just some big circle. And if you look at the curve that we have here, the function is holomorphic in this black region. So in this black region, everything is holomorphic. So because of that, the integral of f of zeta over zeta minus z is equal to 0. And that integral is equal to the integral over big C plus the integral over C epsilon, but going clockwise. So the sum of those two is equal to 0. So that means the integral over big C is equal to the negative of the integral over C epsilon going clockwise. Well, the negative integral going clockwise is the same as the integral going counterclockwise, which is the way we should do things. So let's look at what f of zeta is. F of zeta on the circle C epsilon is equal to f of z plus what? So what comes next?
Epsilon e to the I theta.
Why epsilon e to the I theta?
Well, because that gets us onto the boundary of our circle.
Well, I'm trying to expand f of zeta. So if I'm on C sub epsilon, then zeta is equal to z plus epsilon e to the I theta. Yes.
Just do f primes z minus e.
Okay, so one thing is I could do is it's f prime of z times zeta minus z plus what's next?
Plus
Something like that.
We don't know that the function is differentiable. We don't know f prime is differentiable yet. It is, but we don't know it.
small.
Something small.
Something small.
Wait, why don't we know that? It's holomorphic.
We've never proven that holomorphic implies infinitely differentiable. By the end of today, we will know that. We're not. This is why I truly despise, and this is being recorded, the first part of this course, because I keep having to glance down at my notes where I have reminders to myself. You do not know this yet, Steve. Yes.
Wait, why do we?
We don't. Well, there's a lot of things we don't need. I don't need my industrial strength hairdryer. So
We just need it to be differentiable once.
we don't even need it to be differentiable at all over here. We could just say this equals f of z plus something small by continuity. Does this remind you of stuff we did before, where we first used Grossat's theorem twice, and then for the next one, I could have continued to use holomorphicity, and I needed holomorphicity when I was using Grossat's theorem, but I didn't need actually the full strength. And it's nice to know how strong of a result do we need. I don't need the strength of writing it as some kind of derivative. I can just write it like this. And so now, if I look at the integral over C epsilon of f of zeta over zeta minus z d zeta, and let's just break it up into pieces. It's going to be the integral over C epsilon of f of z over zeta minus z. I can write that as epsilon e to the I theta times I epsilon e to the I theta d theta. And so what's my range of theta? 0 to 2 pi. Then I would have plus the integral over c epsilon. And now the next piece is something small. Divided by epsilon e to the I theta times I epsilon e to the I theta d theta. And so again, I'll do this as theta goes from 0 to 2 pi. So when we look at the first piece, the epsilons cancel, the e to the I thetas cancel, and we just get 2 pi I f of z. I'm basically just integrating the function 1 over z dz. But given that I have z as my center, I don't really want to write it as 1 over z because I've got zeta minus z. It's extremely easy to get confused here. So I wanted to just write it and just see everything cancel. For the next integral, the epsilons cancel, the e to the I thetas cancel, and I'm integrating something small from 0 to 2 pi. So plus something small in absolute value goes to 0 as epsilon goes to 0. Okay. And there we go. And so this is equal to the integral over c of f of zeta over zeta minus z dz, d zeta. I was doing so well. D zeta. And so we get 2 pi f of z equals this integral. So we almost proved the result. I leave the remaining algebra as an exercise. It's not too bad from this point. So we've just proven that if I give you the values of a holomorphic function on the boundary, we know its value at every point in the interior. That's remarkable. Yes.
So let's say if we have multiple keyholes, then do we just like,
So if you have multiple keyholes, what you would do is you would just keep drawing little circles about each one, and then the integral over the entire thing would be the sum. Yes. And so this is going to be a generalization of this. Now, how many bad points do you think I can have? Do you think we can do infinitely many?
countably infinitely?
Do you think we can do countably infinitely many? So finitely, I have no issues with. I'm waving my hands a lot. Countably, yes. I mean, I love the faith.
Oh, sorry, I get too excited, but we can do as many as we can sum in a series, so that would just be countably infinite.
Well, but we start to have to worry about convergence issues with as soon as you see infinity. And I just did this in 349. I mean, why weren't you in my earlier class today? I mean, it's so annoying because I just gave a really nice lecture on it. That whenever you see an infinity, you have to be careful. This is the danger sign. So whenever there's an infinity in play, you should know the infinity could be something blowing up, or it could be infinitely many things blowing up. So if we have infinitely many explosions, that might be hard to do. I'm not saying we can't. We've got a whole semester minus 2 weeks.
Like arbitrarily close to each other.
Well, one of the things is if you have infinitely many points, you have to have infinitely many arbitrarily close to each other if they're confined to be in a unit disk. So you should know this result from real analysis. The Bolzano-Weierstrass theorem. Divide your disk into 4 quadrants and then keep dividing each one, keep dividing each one. You will have to get a subsequence has to converge. So if you have infinitely many points where it blows up, you're going to have a sequence of explosions getting closer and closer and closer to each other. Yes.
we can like draw a line to the center, we can like keep the pattern.
So
you can have like a countable infinitely many set of lines.
So I love the idea that we feel like we can do this, and we can absolutely try later in the semester. Right now, as the designated adult in the room, I am not willing to deal with infinitely many poles. I'm not willing to deal with infinitely many places where it explodes. Finitely many, I am absolutely fine with. And we can easily draw these little disks around them. I have no worries with that. But as soon as we have infinitely many, I now have some grave concerns. Okay. So here is the next beautiful theorem. If f is holomorphic in an open set omega, so this is basically just the standard invocation in all of our proofs. Hey, we have a nice function. Then f has infinitely many complex derivatives in omega. Yay, finally. So after this theorem, we no longer have to worry about, is our function going to be infinitely differentiable once it's differentiable once? And in fact, the derivative, the nth derivative, is just n factorial divided by 2 pi I, the integral over the circle f of zeta, zeta minus z to the n plus 1 d zeta. So not only is it infinitely differentiable, but we have a formula. Have you ever seen anything similar to this result?
It's just like a Taylor series.
It's like Taylor series equation, just telling us what the Taylor coefficients are. But have you ever seen anything similar to this? Maybe earlier today, right? What did we just do? Oh, shoot, there's a, okay, yeah. No, this is fine, okay. So this is f of z related to an integral of f of zeta. And then this is an nth derivative of z related to an integral of f of zeta. And the power down below is n plus 1. What was the power originally? 1. So it looks like what we did over here might just be the case n equals 0 of that theorem. So this actually does look like something we've seen before. Okay. In the proof, there's something that's going to be useful. If I give you, so need for later. Does anybody know how to factor a to the n minus b to the n? Good. It's a minus b times
A and -1.
not b, I think then plus a to the n minus 2b,
Oh, yeah.
right? Plus
All the way
dot 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 plus a b to the n minus 2 plus b to the n minus 1. I know if a equals b is 0, so a minus b is a factor, right? So this is how I know it has to be a minus b times something. So for example, oh, I don't know, maybe I have you know, x plus h to the n minus x to the n. That would be h times x to the n minus 1 plus x to the n minus 2 h plus dot 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 plus x h to the n minus 2 plus h to the n minus 2. So it would have something like this. So if my two quantities are extremely close to each other, the only thing that matters is this is going to be h x to the n minus 1 plus nice times h squared. And so if I looked at, oh, got an x plus h to the n minus x to the n, this should be screaming something to you, right? Divide me by h, take my limit, right? Well, if I divide this by h and take the limit, that's going to just be the derivative of x to the n. And so similarly over here, the only term that would matter would be the leading term. Okay. So we want to prove this. There are two ways to prove this. How many people are taking physics or have taken a high level of physics? Right. There's a one-line physics proof. And I do have a degree in physics, so I believe I am allowed to say stuff like this. What's the derivative of an integral? Yeah, put the derivative inside. It's the integral of the derivative. So just take n derivatives, right? So if I wanted to take n derivatives, I pass the differentiation through the integral, what do we know? Well, we proved this beautiful theorem over here. Let's see if I can copy it nicely. No, I can't because that's a image that I've inserted. Okay. All right. So we know. So we use. So we're using f of z is 1 over 2 pi I, the integral over c, f of zeta over zeta minus z d zeta. And so if I take the derivative with respect to z, I pass that through the integral. F of zeta doesn't depend. This is zeta minus z to the -1. I take the derivative with respect to z, I get -1, and then the derivative of this is going to give me -1, so I get a 1. And this is now going to be to the -2 power. I take the derivative again. I have a -2 exponent that comes down as a -2. I get another -1 from zeta minus z that gives me a factor of 2. And that's where the n factorial comes from. I'm sorry?
How can you take this derivative with respect to z? I thought
Because I have a degree in physics. I mean, weren't you listening? I have a degree in physics. The derivative of an integral is the integral of the derivative. Right? This is the physics proof. My freshman physics professor, who was a great mentor of mine, I remember one day he said, in your math class, it will take 6 weeks to justify the following step. Moving on, we see, and that's the way good physicists often deal with math.
Can you just explain again the n factorial?
Well, just take the derivative n times. When you take the derivative of zeta minus z, so if I take one derivative of zeta minus z to the -1, that's going to be -1 zeta minus z to the -2, and then the derivative of zeta minus z is going to be another -1. So this is just going to be 1 times zeta minus z to the -2. If I take another derivative of zeta minus z to the -1, this is the derivative now of 1 times zeta minus z to the -2. I'm going to get 1 times -2 zeta minus z to the -3 times -1. The -1 and the -2 reinforce, and this gives me 1 times 2 times zeta minus z to the -3. And so you can just keep arguing like this. And that's where you'll get the n factorial. So you have to be able to justify taking the derivative inside the integral sign. But if you can justify that, the proof is very straightforward, right? Unfortunately, I was not able to have this class co-listed with physics. So this is a math class, so this proof is not acceptable, right? So we actually have to roll up our sleeves and we have to do some algebra, right? Does anybody have a thought about what proof technique might be useful to prove that the nth derivative is equal to this? We should proceed by induction. So we'll assume we've done the base case. And in fact, that's what we just proved. So assume true for n, show true for n plus 1. So we have f of n of z plus h minus fn of z over h would be 1 over h n factorial over 2 pi I, right? And then we'll have the integral over c of f of zeta over zeta minus z to the n plus 1 minus f of zeta, sorry, that's zeta of zeta. This is not zeta of zeta. It is f of zeta over zeta minus, oh, sorry. The first one is not zeta minus z. What is the first one? The first one is not zeta minus z. What is it? Zeta minus z plus h. And the second one is zeta minus z. D zeta. And so this is, n factorial over 2 pi I, 1 over h, integral over c, f of zeta, and then I have 1 over zeta minus z, and this was all to the n plus 1 power. So I'm going to write this as zeta minus z minus h to the n plus 1 minus 1 over zeta minus z to the n plus 1 d zeta. Okay. So how can we handle this stuff over here? Yeah, so now go back over here. And so for us, we're going to have x will be zeta minus z minus h, and b will be zeta minus z. Look at that. That's basically going to give us something really nice. So what I want you to do, and this is part to get a sense of how is your algebra, how is your work with sequences and series, finish the proof now. So I'm going to cross multiply. I'll have a zeta minus z to the n plus 1, a zeta minus z minus h to the n plus 1, and I'll have the product of the stuff down below. When h is really, really small, do you agree that these two are basically just zeta minus z? So that's going to look like a zeta minus z to the 2n plus 2. And then when I look at the difference of these two to the n plus 1, or when I expand it out, I'm going to have n plus 1 not n, so I'm going to have the difference h, and then the key part, the zeta minus z to the nth power. So I'll have a zeta minus z essentially to the 2n plus 2. I'll have a zeta minus z to the n. That will give me a zeta minus z to the n plus 2. Oh, that's exactly the power I need. So go through and put in all the details of the algebra. So when you do that, it's going to work out, and in the limit, this is going to converge to exactly what you want it to do. The 1 over h is going to cancel the h from the first term. Everything else, when you expand, when we use these results from the previous page, is going to have an h squared and h cubed and higher. You won't have to worry about them in the limit as h goes to 0, and the integral will just converge to what we want. So again, strongly urge you to do the algebra. When you do the algebra, it sinks in better. It also gives you an appreciation for the physics proof. Much faster, right? But we're just using a really nice identity that, if a and b are close, then a to the n minus b to the n should be close. Okay. So now that we have that, we have some nice results. So one thing is we have some control over how large can the value of a function be. So this is saying that the nth derivative at any point z is at most n factorial times the largest value of the function on the boundary divided by r to the n. So what's nice about this is if r is getting larger and larger and larger, you might be thinking that this is going to imply that the derivative has to be getting smaller and smaller and smaller. What you have to remember is r is the radius of big C. So if r is getting larger, the circle is growing. So what might happen to the largest value of f on this circle? That could also be getting larger. So if you knew somehow that the value of the function on the circle is not growing too fast, if it's growing slower than r to the n, then this would actually imply that all the derivatives have to be 0. Ooh, that could be extremely useful. And we will eventually use something like this to give an analytic proof of the fundamental theorem of algebra. You do not get the designation fundamental lightly. Right? This is not like a participation medal we give everybody for playing as a little kid. Not every theorem gets to have fundamental in front of it. Right? You've got to work to get that. Yes?
It's not like n factorial also goes.
No, because we're looking at a fixed derivative. So if we fix the n, if we fix the derivative we're looking at, then n factorial is just a number. And so the proof is we know fn of z naught is equal to n factorial over 2 pi I, the integral over c of f of zeta over zeta minus z to the n plus 1 d zeta, and I can write zeta as z plus r e to the I theta. So the absolute value of the nth derivative at z naught, let's use less equal to n factorial over 2 pi. And then I'll do the maximum value of f on the circle from the numerator. And I have the integral theta goes from 0 to 2 pi. D zeta is going to be r e to the I theta d theta. And down below, the zeta minus z is going to be, I guess there's an I there, I'll do it slowly, is going to just be r e to the I theta, and I put in the absolute value. Well, notice that everything cancels out, and I just get a 2 pi, which cancels with the 2 pi outside. And so this is just n factorial fc. Oh, and the bottom over here was to the nth power. Oh, sorry, n plus first power. And so then I would get the 2 pi r to the n plus 1. And when I integrate, I get a 2 pi times r. Because there was 1 r upstairs. And so the 2 pi's cancel, and the 1 cancels with the r. And this will just be n factorial, the largest value on the boundary, over r to the n. So this is a nice result about how large can a derivative be. And again, if we have some control over how quickly the function can grow, then this is going to imply serious things. Imagine you knew all the derivatives was 0 from some point onward. Then what would be true about your function? So what would be true if all your derivatives, like your fifth derivative and higher, are all 0? What do you think your function might be? Polynomial of what degree? Nope. Nope. 4, right? So that's what we're hoping to get to. Okay. So the question right now is this enough to prove that our function has a series expansion? No. We now know that the nth derivative is equal to this number. Can we expand everything out and prove that our function is equal to its Taylor series? We know that all the derivatives exist. Is that enough to know that the function equals its Taylor series? Or are you concerned at all from anything you've seen before? Have you ever seen a function where the derivatives all exist, but the function is not equal to its Taylor series? Yes, we saw that example, the e to the negative 1 over x squared. So at this point, we're very close. All we've shown is that if you're differentiable once, you're infinitely differentiable, and we have a formula for that infinite for all those derivatives. But we haven't yet shown that the function equals its Taylor series expansion. We're extremely close. Okay, so we did the Cauchy. So one of the things now is to start trying to apply what we've done to integrate some functions. And so there's lots of functions you can integrate. Your sine squared x over x squared, or 1 over 1 plus x squared. These are both great functions to try to integrate. And so, for example, if I want to integrate sine squared x over x squared dx, x goes from minus infinity to infinity. This function has nice decay at infinity. It's decaying like 1 over x squared. But near the origin, it actually diverges. Or does it? Well, near the origin, sine of x looks like x, so sine squared of x is going to look like x squared. Oh, that's going to perfectly match the denominator. It's actually well behaved at 0. This function is integrable. And so this integral does exist. I noticed when I was taking complex analysis as an undergraduate that this actually equals the integral from minus infinity to infinity of sine of x over x dx, integrate by parts. So I'll leave that as a nice exercise for you to go through. And so you can actually reduce it to a slightly lower dimensional integral to play with. Okay. So I'm deliberately not giving you too many homework problems so that you actually have time to play with stuff like this. You learn a lot by trying a problem and not getting it right the first time or the second time or the third time, and just seeing how can I finally get to the point where I can solve it. So if I do something like this, I could maybe try to use maybe e to the I z over z, or maybe e to the I z minus e to the minus I z over 2I divided by z. And for this, I would take the imaginary part. So I could try to do an integral like that. The problem when you're trying to do something like this is if I'm integrating from minus infinity to infinity, you often go from minus r to r, I'll go down like this, and I'll swing back on my semicircle, but the function is blowing up over here. So because the function blows up, what we typically do is we do a little bit of a detour. And so when we do a little bit of a detour like this, we are now integrating, in a region over here where the function is holomorphic. So what's the integral over that whole region going to be? 0. Now the integral from minus r to minus epsilon, and then from epsilon to r, that's going to converge to the integral we want. So what we'll get is the integral from minus infinity to infinity of sine of x over x dx is equal to the integral from minus r to minus epsilon plus the integral from epsilon to r plus the integral over the semicircle of radius r minus the integral of the semicircle of radius epsilon. Why is it minus the integral over the semicircle? Yes. Opposite direction. We have declared that we always do things counterclockwise. And so when we do the small circle over here, this is being done counterclockwise. No, I'm sorry, not counterclockwise. This is being done clockwise. It's the one up here that's being done counterclockwise. And so what you need to do is you now need to integrate this function, say e to the I z over z, about this circle down here. Well, if we look at what's going on, e to the I z, probably not going to have time to get to the Cauchy distribution today. So we have e to the I z over z. This is e to the I x, e to the minus y over x plus iy. If z is x plus iy is in H, which is the upper half plane, so this means y greater than 0, then e to the I z over z in absolute value is less than or equal to 1 over z in absolute value. And that's because the e to the minus y, because y is non-negative, this is at most 1. And so when we're integrating over the semicircle, the big semicircle of radius r, we know that this function e to the I z over z can't be that large over here. It's going to be at most of size 1 over absolute value of z. Well, how much is absolute value of z if you're on the semicircle? R. So, So if we wanted to do the integral over the semicircle of radius r of e to the I z over z dz in absolute value, and we just naively said that this was less than or equal to 1 over r, d theta. Well, I'll do it as r d theta, because here z is going to be r e to the I theta. Theta goes from 0 to pi. What does that equal? pi, which is not 0. The problem is we were a bit too crude. We're integrating over the semicircle. We have this function, e to the iz. We have this e to the minus y, which we've completely ignored. That has tremendous decay. As long as y is just up a little bit, there's going to be a lot of decay. And so I'll leave you to think about, can we split some of this contour up in a way? So I will go through and I will do a lot of these integrals in full detail in class. I'm going to devote an entire class to doing these integrals. I want you to first, on your own, try to see if you can prove them. We tried to be crude. That's what you should do. Never think more than necessary. I tried to be lazy and I got caught at it. It wasn't enough. I don't need that much more. I just missed. So I just have to be a little bit more clever. So again, I'm mixing things up a little bit. I want you to try exploring a little bit on your own first, and then I will go through and devote some classes to just rolling up our sleeves, and then we'll do all these, literally dotting all the i's. All right. Have a good rest of the day.